Hello, everyone. Welcome to COMPOS webinar number 7 on Hooke's law. Now, Hooke's law is quite simple. It's quite straightforward. I'll just briefly mention, hopefully you're already familiar with it. Now, if you take a spring with the spring constant K, the spring constant simply tells you the ratio between the force and the extension. Basically, spring constant is how much force you need to extend the spring by 1 meter. Most springs don't extend by 1 meter. So it's not a very reasonable thing to say. But yeah, imagine the spring could stretch by 1 meter. And that's the force you need is a spring constant. So you can imagine spring constant for a typical spring is going to be quite large. So the springs that you use in the lab in your school are typically 25 newtons per meter. That means you need 25 newtons to stretch it by 1 meter. But like more often, springs have spring constant 400, 40,000, or 4,000 because you need a very large force to stretch a spring by 1 meter, right? You can imagine that. Now, okay, spring constant. And if you apply a force to this spring, let's copy that spring. And if you apply a force, the spring gets longer. So imagine we're pulling with a force F, and this value is called the extension, delta X extension. Lovely. And Hooke's law basically says that force is K times X. Now, I would normally say minus K delta X because the force it's the force inside the spring. So the spring pulls back. If you pull the string one way, the spring pulls you back, and that's why it's negative. Hooke's law, and then if you draw a graph of force versus extension, force, extension, and it will look something like this until the spring reaches its elastic limit, in which case the graph becomes something like this, and then the spring breaks. Spring breaks. Spring stretches significantly. I don't know if you've ever taken a pen like this and you've opened it up. There's a spring inside. And if you're like me, if you're anything like me, the first thing I did when I realized that there's a spring, I started stretching it. And when you stretch it, at some point it just goes, loses its strength sort of, and just goes. And then you can never put it back together. And yeah, so I'm sure some of you have destroyed pens in the past using that unsophisticated method. So yeah, so that's what happens to the spring on this region of the graph. So this is the stretchy spring. We call it plastic deformation. Plastic deformation. It's called plastic because it does not return to its original shape when you remove the force. Shape not restored. Not restored when force removed. So if you let it go, it stays wonky. And this region of the graph we call elastic deformation. Elastic deformation. And that is where elastic deformation is a string. It goes back. A spring goes back to original shape. Spring goes back to original shape. Shape when force is removed. Force removed. Okay, so there's a question for someone, I'm guessing. Is plastic deformation the same as inelastic deformation? I would assume so. I've never heard the term inelastic deformation. I've only heard the term inelastic collision, but I would assume so. Yeah, yeah, inelastic deformation. And this point on the graph is called the elastic limit. Elastic limit. Well, technically, it's called the limit of proportionality. The elastic limit is slightly beyond that. So typically you would have on the graph, you'd have a straight line going into a curve. And then this point, we call it limit of proportionality. And then slightly beyond is the elastic limit. And somewhere here is the yield point. This is where the spring goes. So it goes. This shows a large deformation without a large increase in force. Basically, the spring gives. It becomes fluid in a way. Limit of proportionality is where the line stops being straight. Elastic limit is the point of no return, where the spring does not return to its original shape. Cool. So let's move. Okay. Now, springs store energy. So we've talked about the force. Springs store energy. Oh yes, I can share the Miro board. Springs store energy, and well, the energy stored in a spring. You can imagine it's the work done stretching the spring. So that's called elastic potential energy. Elastic potential energy, and it's equal to the work done stretching the spring. Okay. If you take a big spring and you stretch it, that means you do work when you're stretching it. And if you let go, it can hit you in the eye. So that's how you can tell that it has elastic potential energy. Please don't hit yourself in the eye with springs, but yes. When you stretch a spring, it stores energy, and you can tell because the spring can fling itself. That means it has energy. Work done by stretching the spring. So let's see what we can do. Well, we know work is force times distance. So if you have a spring and a spring constant K, and you have a force moving F, and if the spring moves a small distance, that's your distance moved, right? Distance. So work is force times distance. Problem is the force keeps changing because there's the more you stretch the spring, the more force you need. And that's what we see on the graph. The force increases as with distance. So the more distance you cover, the bigger the force. That's not very helpful. How can we calculate force times distance if the force keeps changing? Well, we use a very important, a very, very important tactic. We say, what if the force doesn't change gradually, but the force changes in jumps? So imagine force changes in jumps. So sort of gradually, but not really gradually. So imagine the force starts with 0, then increases like this, like this. Right. I hope that makes sense. So basically, the force is not increasing gradually; it just goes rook, then suddenly increases, etc. But the beautiful thing now is that we can say that during this sequence, the force, let's call it F, let's call it F1, let's call it F2, F3. The force is F3 multiplied by the width. So let's call it delta X. So the work, not delta X is a bad example. D1. Let's call it D3. Let's call it D2. And this is D1. Work is equal to for F3 times D3. But F3 is the height of this rectangle, and D3 is the width of this rectangle. So that's just the area of the rectangle. Interesting. So the work done here is equal to that area. And the work done here is equal to that area and that area. So what I'm trying to say is the work done is approximately work done is approximately the total area of rectangles. Okay. Simulation data. Okay, so here's a graph, and you can see that the green area is approximately equal to the area. Sorry, the green area. So once again, the black line is the actual force. Actual force. And this is the force, and this is the extension. We say, but instead of thinking of the force like it, we assume that the force just goes in jumps. So it goes bam, 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 like this. So here, for example, let's say this one, F is 0.5, and the distance is 1.25 to 1.7, so 0.5. So the work is 0.5 newtons times 0.5 meters, which is 0.25 joules. So the work here is 0.25 joules, and it's also equal to the area. Sammy, yes, you're correct. It is easier. But how do you know that the area of the triangle is equal to the work done? I know in a school book they will just tell you that. But I'm I'm explaining why it is so. Right. So if you add all of these rectangles, that's approximately the work done. Approximately because we approximated the force. So total work is approximately the total area of rectangles. Does that make sense? Do you understand what, on a scale of 0 to 10, please type in the chat. Do you understand what I do? Potential energy, you calculated the extension, no, not the total length. Okay, now going back to this, I'm going to make the rectangles narrower. And would you look at that? I've made the rectangles narrower, and now the area under the black line is closer to the total area of the rectangles. If we increase the number to 100, I think very few people can tell the difference. Make the rectangles narrower. Make the rectangles much narrower. So add more rectangles, add more rectangles, add more rectangles. So now we can see that the work done is the area of rectangles, which is also the same as, well, approximately the same as the area of triangle, which is the area under the curve. So bottom line is work elastic potential energy is equal to the area under the graph. And a lot of you will just say, well, yeah, we knew that before. Well, yes, you knew that before, but I doubt that somebody explained to you why it is so, right? So if you knew this before, but you didn't know how to explain it, can you type 1 in the chat, maybe, just for me to understand? And if you no, the force does not go in jumps. The force goes gradually. Like here, we can assume that it goes gradually, but uh, going up gradually or going up in very, 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 very small jumps is the same thing, isn't it? Well, the further you pull, the harder you need to pull, right? If you're just starting to stretch the spring, you only need a small force. If you stretch it by more, it's you need more force. The more you stretch it, the more force you need. Okay. Area under the graph. And elastic potential energy. So if the extension is delta x, so the extension is delta x, and the force is F, and then the area is 1/2 F delta x, and that's the elastic potential energy. Elastic potential energy is 1/2 F delta x. Now, it also kind of makes sense because the average force is half the maximum. That's why it's a half. Because we start with 0 force, we end up with F force. Therefore, the average force is a half. But remember that F is K delta X, so we can substitute that in. The elastic potential energy becomes 1/2 K delta X squared, which looks a little bit similar to half mv squared. And not entirely a coincidence that they look similar. They look similar for a for a very similar reason. Let's put it that way. Anyways, all right, we've established the area under the graph is the energy stored or the work done stretching the spring. The gradient is of course the spring constant. Gradient is K. Why is delta x squared? Well, because if you take this formula, 1/2 f delta x, and f is k delta x. That's 1/2 k delta x, which is 1/2 k delta x squared. That's the reason. You can't. What is x? X is the extension of the spring. Delta x is the extension of the spring. X typically is the coordinate. It doesn't matter how you can say. It depends on your definition. How do we define in an assignment? Let me just double check the assignment. Do we say x or delta x? Okay. Sorry, in our assignment we do use x, so we can we don't have to use delta. Okay, let's modify our. It's the same thing. It's a matter of which letters you use. So I just tend to use delta x, but it doesn't matter. Okay. Okay. Delta x. Delta x. Just let's make it less confusing. Okay, thank you. I hope that makes sense. Delta x. Look, it's in some books. In some books, x is extension, and in some books, x is length, and delta x is extension. And L is length, and x is extension. So extension can be written down as x or as delta x. Both are correct. So you just need to choose the one that you like and you use it. Okay, so it's not a mistake to use delta x as long as you understand what it means, right? That's why in GCSE you often are asked to write down the formula in words, right? Because the formula can be written as 1/2 kx squared or 1/2 k delta x squared, or even in some cases 1/2 k e squared, because some people use e for extension, and that's fine. It's not a big deal. Okay. Right. So basically, it's the same thing. So let's stick with x. So I won't make it more confusing than it should. All right. So x is extension. Lovely. A spring of natural length 20 centimeters extends to 26 centimeters under a 12 Newton load. It's a very easy question. Estimate the spring constant and determine the force needed to compress it to 17 centimeters. So the spring is 20 centimeters long. 20 centimeters long. And when a force is applied, it becomes 26 centimeters. So extension is 6 centimeters. And the force is 12 newtons. 12 newtons. Therefore, so the spring constant, 6 centimeters, 0.06 meters. And that is, so we write down F equals kx. Force is 12 equals K, which is K multiplied by 0.06. K is 200, I guess. Double check. At the end of the day, I'm not very good at mental arithmetic. 200, yes. 200 newtons per newton per meter. Newtons per centimeter. Yeah, that's fine. You can use newtons per centimeter. Newtons per meter. So that spring constant means that to extend the spring by 1 meter, you need 200 newtons. That's what it means, this the spring constant. Determine the force needed to compress it to 17 centimeters. Compress it to 17 centimeters. So extension, extension. So this is question A, and this is B. Compressing to 17 centimeters. Extension is going to be the final length, so 17 centimeters minus 20 centimeters, which is minus minus 3 centimeters, which is minus 0.03 meters. And of course, the force is K times X, which is going to be 200 Newton per meter times negative 0.03 meters, which is going to be 6 newtons. That is minus 6 newtons because it's the opposite way. Now, the minus sign is very arbitrary. Like, I mean, technically, I should have written minus kx here and then say the force must be negative 12. But it's sort of, you work with modulus here. You don't need to worry about the sign. Like, really, like as long as you understand which way the force is, you can just write the force is that way. Because saying force is +5 or -5, well, what do you mean that the force is -5? Do you mean that the force is down? But who told you that down is negative? It's up to you. It's your choice which way is positive, which way is negative, because you are modeling the situation. I hope I'm making sense. Like, people say G is minus 9.8. Well, yes, if you assume that up is positive, but if you assume down is positive, then G is plus 9.8. Right. So hopefully that makes sense in some sort. Okay. Then the next now we're jumping into much harder problems. So apologies. We've done an easy one. Now let's get to grips with some tough ones. Find the effective spring constant. Well, if two springs are in parallel, so K1 and K2, then the total spring constant is just K1 plus K2. It's very similar with resistors, except it's the other way around. Parallel resistors, you go down. Series resistors, you go up. Here it's the other way around. If you have two springs in series, then K1 and K2, the total, so 1 over K total is 1 over K1 plus 1 over K2. But this formula can be rewritten. So if you, from here you can find the common denominator. So 1 over k total is k2 plus k1 divided by k1, k2, which is k total is k1, k2 divided by k1 plus k2. Quite a useful formula as well. Okay, so springs in parallel, springs in series. So this is parallel, and this is in series, and this is in series. Okay, so here we have two springs in parallel. So this spring can be replaced with one spring, which is K1 plus K2. So here we go K3. This is K1 plus K2. And this is K4. Right. So this is, so basically you can replace two parallel springs with one. Now for this series combination, to find this is K, let's call it K, K top. Okay. K top is using the formula. So it's K3 multiplied by K1 plus K2 divided by K, sorry, it's K1 plus, no, that doesn't make sense. So multiplication divided by K1 plus K2 plus K3. Yes. Okay. Which can be simplified as, well, you don't need to simplify it yet. Okay. And then we have two springs. How did you do this fraction with K total? Let me show you. This is K4, and this is K3, K1 plus K2, divided by K1 plus K2 plus K3. Okay, so let's recall resistors in parallel. 1 over R total is equal to 1 over R1 plus 1 over R2. We multiply, well, yeah, let's multiply by R1, R2. Everything multiplied by R1, R2. So R1, R2 divided by RT is equal to R1, R2 over R1 plus R1, R2 over R2. Cancel the R1s. Cancel the R2s. So we get R1, R2 over RT is equal to R1 plus R2. And then, well, we kind of divide by that. So we divide by R1 plus R2 and multiply by RT. So you get R1, R2 divided by R1 plus R2 equals to RT. So that's the formula. And exactly the same thing for springs in series. So 1 over K total equal 1 over K1 plus 1 over K2. So we multiply both sides by K1, K2. We get K1, K2, K total equal to K1 plus K2. K total is K1, K2 over K1 plus K2. Does that answer your question? Okay. And then we just, because they are in parallel, now we just add them up. So we have the effective spring constant. So we can replace this by a single spring with spring constant K4 plus K3, K1 plus K2 over K1 plus K2 plus K3. And then the combination, so answer, the effective spring constant is K4 plus K3 multiplied by K1 plus K2 divided by K1 plus K2 plus K3. You could put it into one fraction, but I honestly wouldn't, because that wouldn't make it easier in any way. That's it. That's the answer. Okay. A spring is cut into two pieces, L1 and L2. Right. So a spring is cut into two pieces, L1 and L2. And the spring constant of the spring is K. Find the spring constants of each piece. This is K1 and this is K2. Right. Well, first of all, why would the spring constant change? Like, wouldn't you just have two springs with the same spring constant? Well, obviously not, because if you'd have two springs with spring constant K, the total is going to be K over 2, not K. So therefore, K1 and K2, K1 is not equal to K, and K2 is not equal to K either. Right. Okay. So what 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 do we have? Well, imagine that we have this spring. Instead of one spring, imagine we have two springs, K1 and K2. And let's pull on it. Let's pull on that spring with a force F. Force F. So the force is the same for both springs, so K1. So the first spring extends X1 by F divided by K1. And the second spring, X2, extends by F divided by K2. So it's the force divided by extension. All right. Now, but we know that the total extension is X, right? Total extension is X, which is the force divided by X, by the original K. Okay. But we also know that the longer the spring, the more it extends. We know that X1 to X2, the ratio of extension is going to be L1 to L2. So we can sub that into here. So X1 to X2 is equal to F over K1, F over K2, and that's L1 to L2. And that means that K2 over K1 is equal to L1 over L2. In other words, we know that K2 is L1 over L2 K1. And we're going to use that. And we also know that the spring, so the total extension is F over X. We also know that x is x1 plus x2. So from here, we get f over k is equal to f over k1 plus f over k2, which is obviously 1 over k equals 1 over k1 plus 1 over k2. Okay, and from here, I can substitute k2. Do I want to do that? I think I do. Yes, k2, substitute that in to here. So 1 over k equals 1 over k1 plus 1 over L1 over L2 k1. I can take this KL2 over here. Okay, so 1 over k equals L1, so 1 over k1 plus L2 over L1 k1. I multiply this by L1 multiplied by L1, and I get L1 over k equals L1 plus L2 over k1. Okay. And here I can write k1 is L1 plus L2 divided by L1 multiplied by k. Wow. Okay. And from no, we're looking for k1 in terms of k. The task was to find k1. Right. Now, k2 is of course L1 over L2, k1. So I just substitute L1 over L2 multiplied by L1 plus L2 divided by L1 multiplied by K, which is L1 plus L2 over L2 times K. So K2 is L1 plus L2 divided by L2 times K. Right. So we found the spring constants of the two springs. Okay, so we have K1 is L1 plus L2 over L1 K, and K2 is L1 plus L2 over L2 K. Now let's verify that 1 over K1 plus 1 over K2 is 1 over K. So 1 over L1 plus L2 over L1 K plus 1 over L1 plus L2 over L2 K is, okay, so L1 goes on top. So if you have a double fraction, it goes on top. So it's going to be L divided by L1 plus L2 K plus L2, so L2 divided by L1 plus L2 K. And then I add them. They have the same denominator, so it's going to be L1 plus L2 divided by L1 plus L2 K, and then this cancels out, and it's 1 over K, so true. Okay, so I hope that makes sense. Now, if you found this question difficult, I have bad news for you because the next one is even tougher. But it is incredibly similar to the one in the assignment. So I'm basically giving away the solution. Right, so I'll need more space. So we have we have a lot of springs put together, and we need to find the effective spring constant. The problem with this is that these springs cannot be broken down into parallel and series, like, no matter how you try. So you have to do it from the first principles. You have to say, well, what if I apply a force F, and this end is fixed, of course. Well, obviously, the force on the other end is also F because, I mean, the system is in equilibrium. So if you pull that F with one way, it has to be F going the other way. And each spring extends. And let's call this extension X1. We'll call this extension X3. This is X3. Because of symmetry, you can see that these two springs extend by the same amount. So we can say extension in the spring is X3, X1, right? The extension is this spring is X4, and the extension is this spring is X4. Now, when you extend, the total extension is X. So we can say that the extension is the extension in spring X3 plus the extension in spring X4, right? Because if you extend, you can see that these spring, and if this spring extends by X3 and this spring extends by X4, the total extension is X3 plus X4. So the whole system gets longer by X3 plus X4. On the other hand, the whole system extends by X4 plus X1 plus X4. X is X4 plus X1 plus X4. So this is if we go this route. Bam, bam, bam. So this is X4, X1, X4. So if I stretch the whole system by X, the total extension X is X4 plus X1 plus X4. Okay. By the way, last year I did a simpler webinar. So if you're really confused today, do watch my previous webinar. Hopefully that you can pick something up from there. And that's the first thing. Then the force. Let's talk about the force. The force in the this spring. Let's call it F3, F4, F1, and F3, and F4. Well, F, obviously the external force, is pulled by these two forces. So F is F3 plus F4. And on the other end, it's also F3, F4. Okay. On the other hand, F4 is F3 plus F1. F4 is F3 plus F1. Okay. I think we have enough. And let's not lose our aim. Our aim, find F divided by X. F4 plus F3. What did I say? F4 is F1 plus F3. Because look, this point is in equilibrium. And it's pulled this way by a force F3. It's pulled this way by a force F1. And it's pulled this way by a force F4. So you can see that F4 is F3 plus F1. And the same here. This point is in equilibrium. It's pulled by a force F this way. It's pulled by a force F3 this way. And it's pulled by a force F4 this way. I think we have enough enough equations. So let's solve. Basically, this 4 equations. We need to solve them. There are 3 unknowns. X1, well, 4 unknowns. X1, oh yes, 4 unknowns. So x1, x3, x4, and yeah, 3 unknowns. That's lovely. Cool. But we know that f1. So yes, sorry, I forgot to mention that because we know f1 is k x1, f2 f3 is 3k x3, and f4 is 4k x4. Okay, so of course we'll substitute those in. So from here I get the four equations. X is x3 plus x4. X is x4, 2x4 plus x1. Then f is kx equals 3kx3 plus 4kx4. And lastly, 4kx4 equals 3kx3 plus kx1. Now k cancels in both equations. And hopefully we get something reasonable. X is x3 plus x4. X is 2x4 plus x1. X is 3x3 plus 4x4. 4x4 is 3x3 plus x1. Okay. x4. What can we do here? Well, we can find x4 is x3. Ah, lovely. Would you look at that? If we do x4 is equal to x minus x3, and we sub it into here. So x is 3x3 plus 4, x minus x3. We can get x equals 3x3 plus 4x minus 4x3. And from here we can get, well, we can get minus 3x equals minus x3. So x is x3 is 3x. That doesn't make any sense. What did I do wrong? Minus 3x, 4x. That can't be true. Okay, let's double check. So the first x3 plus x4 is x. x3 plus x4 is x. 2x4 plus x1 is x. Right. So x4 is x minus x3. Cool. And then kx is x is 3x3 plus 4x4. X is 3x3 plus 4x. 3x is equal to x3. can't find a mistake. I mean, this is nonsense because x3 cannot be 3x. Right, what time is it? It's almost 7. Do you mind if we leave it? If we leave it like this? Well, we are using force and we're using. Oh, you mean F's? Just a second. F force is kx1. Okay, 3k x3. Yes, F4. So F is F3 plus F4. Yes, definitely. F4 is F1 plus F3. It has to be true. Yes. Ooh. Uh, yeah, that shouldn't matter. We assume that all of them stretch. All of them stretch, so all of them pull. Where does x minus x? Well, I'm just solving for x this. So this is 3x3 minus 4x3. It's minus x3 minus 3x. Sorry, I'll have to leave it. I'll have to leave it because I've made a mistake somewhere and I can't find the mistake. And I think finding it will take me a longer time. So if we have time, we'll come back to it, but I doubt that we'll have time to go back to it today. But the idea is you have 3 unknowns. So your unknowns are x1, x3, x4. x1, x3, x4 are unknowns. And you are writing down equations. You're writing down a system of simultaneous equations where you can see that x3 plus x4 plus x4 is equal to x to the total extension. And then x1 plus 2x4 is also x. And then the forces, so you've considered the forces. So here F4 must equal to F1 plus F3. And F must equal to F4 plus F3. And yeah, so it's just, and we also know that F1 is KX1, KX1, yes. Okay, and F is equal to F3 plus F4. Oh, sorry, F3 is 3K times X3, and F4 is 4K X4. So that should be right. And if you solve these equations, you get solve. Okay, I'll leave it to you. But I've made a mistake somewhere. I'm not sure where. Let's move on to the next question, problem 5. It's easier, much easier. Right, so, oh, that's the wrong one. Where is the correct one? Where is my... It's quite an interesting question. Right, so we have a copper rail of cross-sectional area 3 centimeters. So it's very similar to one of the questions from the assignment. And it's Well, I don't know if you can imagine, like if you take a piece of steel and you hammer it in, so you fix a piece of steel or a piece of metal onto the ground in the summer when it's longer, right? Then when the winter comes, it will shrink. It will try to shrink. But because it's fixed in place, there will be tension inside. Okay. So we need the Young's modulus. We need to stress and strain. So um, let's call it stress is force divided by cross-sectional area, and strain is the extension divided by the original length. These are the two things. So stress, that's force divided by area. And strain, for stress, we use a Greek letter sigma. Sigma. And for strain, we use the Greek letter epsilon. Epsilon is the extension, is x divided by original length L. So, and the Young's modulus Y is stress over strain. Stress divided by strain. All right, so here we we have a rail, cross section A, so some sort of this, 3 centimeters squared. Right. Is fixed at both ends during the summer when the temperature is 22 degrees. Find the tension in the winter. So T or T1, T2 is minus 10 degrees Celsius. And the thermal expansion coefficient alpha is 1.7 times 10 to the minus 5 Kelvin to the minus 1. Why does the tension depend on the rail's length? Okay, so we assume that the length of the rail is L. Now, first of all, let's find by how much the rail should shrink. And the amount that it should shrink by delta L, which is the change in temperature multiplied by the original length multiplied by alpha. Okay, which is the change in temperature is 32 degrees. 32 degrees multiplied by 32 Kelvin multiplied by the original length L multiplied by 1.7 times. Oh, you know what? I'm going to leave it like this. I won't use any numbers yet. Okay. This rail should shrink by delta L. This means that the pegs that hold the rail in place, the pegs that hold the rail, produce tension. So the rail is longer than it wants to be. So the rail is trying to shrink. So what force do you need to keep it the same length? And that force, force is the Young's modulus multiplied by the strain. sorry, Young's modulus is stress over strain. And we know that stress is force divided by cross-sectional area, and strain is the extension divided by original length. So from here, we can say that extension is, well, we can say y is FL over AX. X is AY divided by FL, where A is the cross-sectional area, Y is the Young's modulus, F is the force, that you need to stretch the rail, and L is the original length. On the other hand, but this is the extension. It's the same thing. The rail should shrink by delta L, and you need a force F to extend it by X. Ooh, that doesn't make any sense. Sorry. AY. No, FL over AY, of course. It's the other way around. FL over AY. Okay, sorry. And then you can yes, this is A level stuff. And so you can make them equal to each other. So delta L is equal to X. So delta T times L times alpha is equal to FL over AY. L cancels out. And the force is change in temperature times alpha times the cross-sectional area times the Young's modulus. And we just need to check the Young's modulus for copper. Young's modulus copper. 100 and let's say 120 gigapascals. Young's copper is 120 gigapascals. So the force is the change in temperature times alpha times A times Young's modulus, which is 32 degrees Kelvin multiplied by alpha, which is 1.7 times 10 to the minus 5 Kelvin to the power minus 1, multiplied by the cross-sectional area, which is 3 centimeters squared. So 0.03 squared meters squared, multiplied by the Young's modulus, which is 120 times 10 to the 9 pascals. And you can see that Kelvin cancels out. Pascal is Newton per meter squared, so meter squared cancels, and you are left with newtons. And that is just 32 times 1.7 times 10 times 10 to the minus 5 times 0.03 squared times 20 times 10 to the 9. 58,800 newtons. That's a strong force, but it's independent of this force is independent of the length, because you saw that length cancels out, independent of length. And this answers a very important question. I don't know if you've ever thought about it, but modern railways do not have expansion gaps. So expansion gaps, railways. Right. So in the olden times, well, not so olden times, railways used to have expansion gaps like this. Why so? Because in the summer, the rail becomes longer. In the winter, the rail becomes shorter. And you need to leave a gap for that expansion. Otherwise, everyone thinks that the rails would go like this. They would go wobbly because they would become too long. And that is why if somebody says, can you make a train sound, but not choo-choo, they say it's choo-choo, 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 choo-choo. That's the wheels hitting the expansion gap. Choo-choo, choo-choo. The wheels come in pairs. Choo-choo, 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 choo-choo. And that's why you hear that sound, but there's no more sound. It doesn't exist anymore. And the reason for that, because modern railways don't have expansion gaps, no expansion gaps, and the reason for that is that the rails are laid and they are hammered to the ground, and in the winter they just extend. They extend from the force of the tension. So in the winter they are under tension, and in the summer when it's hot they're under compression, and it's perfectly fine. Railways are allowed to be under compression or under tension. They don't expand uncontrollably. And there's an amazing video by Veritasium on how the train tracks are laid. It's quite fascinating. So if you're interested in engineering, do check that out. So it's Veritasium. Why do railways don't have expansion gaps? Right. Now, number 6. A long elastic band of Young's modulus Y, cross-sectional area A, natural length L is stretched to 1.1 L. Find the total stored elastic energy. Okay, so we have an elastic band, which is like this, and cross-sectional area A, and natural length L, and you stretch it, the force, and it becomes longer. It becomes longer by 0.1 L, apparently, but because it's stretched to 1.110 L. So the strain is the extension divided by the original length, which is 0.1 L divided by L. So that's 0.1. Stress is equal to the force divided by the force divided by cross-sectional area. And the Young's modulus, we know that it is stress over strain. So it's stress over strain. Stress, strain. And we have F divided by A divided by the strain, which is 0.1. So it's F divided by 0.1 A. And but we know this Young's modulus, so we know the force. So hence the force is 0.1 A. Okay. Y. And then elastic potential energy. We already know that it is 1/2 F times X times the extension, which is 1/2 multiplied by 0.1 AY multiplied by the extension, which is 0.1 L. And so that is 0.01, 0.005 A L. And that's the answer. Okay. And of course you can see that the longer it is, the more energy is stored. A two-spring mechanism has springs K1 and K2 arranged in series. So we can say that we have two springs, K1 and K2, and we it oscillates like this. It bounces left and right, oscillates. And the amplitude is A. So amplitude is the maximum displacement. So let's have a look how it looks like. Fed, springs, oscillations, springs and masses. That should work. That should work. Yes. So if we take a two spring, can we have two springs? No, they don't allow us two springs. But anyways, if you like this, okay. Except now we have two springs in series, but the principle is the same. The amplitude is the maximum displacement from the equilibrium position. So this is the equilibrium position, and this is the amplitude. So if I stretch it to here, it will oscillate with this amplitude. So in this case, the amplitude is about 20 millimeters. Okay. So the mass oscillates 20 millimeters each way from the equilibrium position. So hopefully that makes sense. Okay, so the amplitude is A. So when the spring is at maximum displacement, it both the total stretch is A. A is the amplitude. Well, we know that the effective spring constant is K, which is K1, K2 divided by K1 plus K2. And so the well, yeah, that's it. So the elastic potential energy is 1/2 F times delta X, F times the extension, and the extension is the amplitude, is the maximum, is how far you take, and F is kx as well. So it's 1/2 kx squared. So it's 1/2 k1 k2 divided by k1 plus k2 multiplied by the amplitude squared. And that's the elastic potential energy stored in each spring. Sorry. Ooh, okay. And that's the total elastic potential energy. Okay, that makes sense. So effective spring constant is this. All right. So that's the total energy. So that means the force in the spring, when the spring is at maximum displacement, so at maximum displacement, the force in the spring is the spring constant divided the effective spring constant. The at maximum displacement, the force is the effective spring constant multiplied by A. Spring one, the elastic potential energy in that spring is 1/2 of the force multiplied by the extension of spring one. And okay, so it's for spring one is this. Now the force is the same, and now the extension of spring one is the force divided by K1. So that's going to be K effective times A divided by K1. And that is K2A divided by K1 plus K2. So that's going to be 1/2 multiplied by, well, K1 multiplied by X1 squared. Let's use this formula. So it's 1/2 multiplied by K1 multiplied by K2A divided by K1 plus K2 squared. And spring 2, the elastic potential energy 2 is going to be 1/2 K2 multiplied by X2 squared. And X2 is the force divided by K2, which is the K effective times the amplitude divided by K2, which is K1A divided by K1 plus K2. And that's 1/2 multiplied by K2 multiplied by K1A divided by K1 plus K2 squared. Now let's see if that actually adds up. So let's add those up. EP1 plus EPE2, and that's equal to 1/2 K1 K2 squared A squared K1 plus K2 squared, and then plus 1/2 K2 K1 squared A squared K1 plus K2 squared, and that's equal to 1/2 K1 K2 squared A squared plus K2 K1 squared A squared divided by K1 plus K2 squared. Okay, so that's 1/2 K1 K2A divided by K1 plus K2 squared multiplied by K1 plus K2. This cancels, and we're left with 1/2 K1 K2 K1 plus K2 A squared. Yes, I think we got it. Got the same expression. Yes. And then, unfortunately, we don't have time to do the last question. Just a few words. So a steel ball. Actually, we just might. Okay, wooden block attached to a spring. Determine the maximum compression of the spring. So we have a wooden block and a spring, and we have a steel ball traveling. Mass is 12 grams, traveling at 600 meters per second. Block is 1.2 kilograms, and attached to the spring. This determine the maximum compression of the spring. Well, we need to find the kinetic energy of the block. So once the pellet hits the block, it embeds itself in the block. So the pellet and the block move together with a speed v. And we use conservation of momentum. So m1 v1 plus m2 v2 is equal to m1 plus m2. That's the total mass, was plus m2, multiplied by v. And then we can work that out. We can work out v. V is m1v plus m2v2 divided by m1 plus m2, which is 12 times 600 plus 1,200 times 0 divided by 1,212 grams. I'm doing it in grams. And so that's going to be times 600 divided by 1,212. 6 meters, 5.94. 5.94 meters per second. That's the speed of the block after. So we can find the kinetic energy. Kinetic energy is 1/2 mv squared. So that's 1/2 times 1.212 times 5.94 squared. So squared times 1.212 times 0.5, which is 21.386 joules. That's the kinetic energy, and the elastic potential energy. So with the block moves with kinetic energy, and then it stops when the spring is compressed. So the kinetic energy goes into elastic potential energy. So the elastic potential energy is 1/2 k x squared, which must equal to kinetic energy, and therefore 1/2 k times x squared is kinetic energy. So x squared is 2 kinetic energy divided by k. So x, the maximum displacement, is square root of 2 times kinetic energy divided by the spring constant. And what is the spring constant? Is 250. So it's 2 times 21.386 square root divided by 250. And that gives us square root of 2 times ounce over 250. 0.414 meters. So quite a lot, right? But it is quite a fast speed. So the pellet hits the block. The block moves, compresses the spring, and kinetic energy transforms into elastic potential energy. Right. I'm very sorry. I have to rush away. I'm gonna make a lot of people mad if I'm late. And yes, so thank you very much for staying with me today for the whole session, and see you in 2 weeks' time.